did it, y'all. This is the last day of the programming segment of CS54, the last one. So with the homeworks from today, day 10, and from day 9, we'll be adding just like a little bit extra to be the take-home midterm. Then after that, we're going to do a big change of topic. So with the last video here, we'll get to take a deep breath and move on. Okay, so what are we going to talk about today? Today we're going to talk about a subject that's very dear to my heart. We're going to talk about how computers represent programs. We're just going to dip our toes in the water, but we'll sort of get a nice sense of how to think about representing programs and how we execute them and manipulate them. This is actually my area of research. It's a thing that Coq gets used for all the time, and it does a pretty good job at it, though lots of languages can implement other languages. So we're going to look at a very, very simple language, just a language of simple arithmetic and Boolean expressions. Right? So that's a language that's going to let us do some math and let us do some comparisons on that math. That's it. It's hardly a programming language, but it's I think a perfect setting for us to get a sense of just the bare ideas here. Let's get started. So we're going to start with a very simple version of our language. I've defined two data types here, and these are our abstract syntax trees. So they're abstract because we're not representing the concrete syntax of a programming language, right? In Coq, you write, there's all these keywords and there's colons and there's this and that, right? But under the hood, the computer represents them in a simplified way. For example, we don't care how much space was somewhere or whether a new line was here or there, right? All that stuff is important, and it'll be somebody's job to sort of check on all that while translating to the abstract syntax tree. But the goal of the abstract syntax tree is to be abstract, meaning that it's not going to keep track of sort of irrelevant detail, just the sort of semantically relevant bits of your. So, for example, here for arithmetic, our notion of an abstract expression is, well, what can an arithmetic expression be? It could be just a number. It could be the sum of two other arithmetic expressions. Notice there's two parts here. They're just written next to each other because type. It could be one arithmetic expression subtracted from the other. We'll read this if it's asymmetric going from left to right. So it'll be, this would represent, okay, whatever A1 is, and then you would subtract A2 from that. And then lastly, the multiplication of two arithmetic. Okay, let's take a second to process this, and then we'll go back and look at what bx means. Like, let's look at an expression like 1 plus 2 times 3. Now everyone's getting out there like their PEMDAS notes and being like, this is like those awful social media, like, they're online. Like, okay, fair enough. So the conventional interpretation of this is that multiplication takes precedence over addition, so we should really interpret it like this. Right? This is 1 plus 2 times 3, right? The sum of 1 and the result of multiplying 2. And we would represent that using our abstract syntax like this. The sum, a plus, of the number 1 and the result of multiplying 2 times 3. This corresponds to a tree that looks a bit like this. Okay. So this process that takes a string and turns it into a tree like this, or like the notional tree that we have that diagrams like this in mind, this process is called parsing. We're not going to talk about it in this course at all. You'll probably interact with parsing at some point in 105, having just worked with some data. Maybe yes, maybe no. If you take 131 or one of my electives, you'll almost certainly interact with parsing. Parsing is one of the most important topics in computer science because data that humans use is always in this stringy form, right? Like our written text we communicate with each other is all written in strings. Your programs in Coq are just text, right? So for the Coq compiler to be able to adequately work with your program, it needs to parse your program. So getting good parsers that are fast and correct and sort of let you parse a robust and interesting language, all these are really, really important things. Almost every programmer I know, whether they're working at the lowest level or the highest level, right, down close to the chip or, 7 layers of abstraction deep in a web browser, everybody has to think about parsing. It also turns out that parsing is hard, which is part of why we're not going to do it. I'd be delighted to talk with folks one-on-one if they're curious about the process at all. Let's pop back up. We got from this string to this tree by interpreting the constructors we have up here. So we said, okay, we had a plus there, and it was going to be outermost. So if we needed precedence, then it would be tighter in the tree. So notice how the mult is lower in the tree than the plus is. Right? This mult tree is really this subtree, and that's sort of representing that we really wanted the print. Okay, let's look at bx. So Boolean expressions, what counts as an expression that's a Boolean? So you'll notice all of these are things that like implicitly should, when if we computed them, would be a number. These are all going to be things that if we computed them would be a Boolean. So okay, what do we have there? We have true and false. Right? We have a test for equality on two arithmetic expressions. We have a test to see whether one arithmetic expression is less than the other. We have negation, right? This will be true when, will be interpreted as true when this one is false and vice versa. And we have conjunction. Okay, let's do a series of short quizzes, not because I expect you to have immediately gotten this, but because I think this is the best way to have you learn it, right? So I have a series of quizzes where I'm going to give you some strings. I'm going to ask you what AST it turns into, and then similarly, I'm going to give you some ASTs and ask you to turn into a string. So let's get started. I think it really is worthwhile. Like, don't just like run the video and have me tell you the answer. I think it's really worthwhile for you to spend really as long as you need, a minute or two, five even, to try to figure it out and come up with what you think is your best guess. Because I think that'll be the way that you'll learn how this correspondence works the best. Okay, let's get started. What AST corresponds to 1 plus 2 times 3? Pause the video if you need to. Okay, this one was designed to be pretty similar to this one, right? It'll be like this, except for, well, wait, we want the 1 and the 2 to be summed, and then you just multiply that by 3. That'll look something like an AX. Let's write the type, why not? So it's going to be a mult, a plus, a num, 1, a num, a num. Okay, so notice again how this is the bit that's lower in the tree. We'll sum up 1 and 2 and then multiply that by 3. So we're using the tree to sort of, writing things down as a string, we use parentheses to indicate precedence. Once we've parsed it into such an AST, here we're the ones doing the parsing, not a program, uh, then we'll just use the structure of the tree to communicate any ambiguities that might be there, right? Given just this string, someone who doesn't know PEMDAS might say, well, look, did you want this tree or did you want this tree, right? And it's a parser's job to disambiguate those. So we end up having rules of precedence saying like, oh, well, look, if you're not sure, you put the parentheses here. So here, because we've said we want 1 plus 2, the quantity to be multiplied by 3, we'll put it there. Okay, let's keep going. What AST corresponds to 2 plus 2 equals 4? Pause the video. Okay. First thing you should notice, well, okay, this is an equality comparison, so we should be, well, this is an arithmetic expression, and this is an arithmetic expression. But here, we're going to need to do something involving equality. So let's hop back up, get a look at our constructors for bx. This seems like a strong candidate. We said this was going to represent equality. Okay, so let's try it out. Okay, it's a bx, and it says b eq. You'll notice we've put the letter before the different constructor names just to sort of remove any ambiguity about which kind of thing you're building, which kind of expression. Okay, and then now it takes two arithmetic expressions, a1 and a2. So we want to check that a plus a num 2, a num 2 equal to a num 4. Okay, you might have gotten something where you swapped the sides, right? Maybe you had a num 4, a plus a num 2, a num 2. And like, I have a lot of sympathy for writing this. This makes a lot of sense to me to want to write it this way. Sure. Should be the same, right? It's about equality. I want to warn you against that. So the abstract syntax tree is meant to reflect all of the essential information, but at this point, we've sort of changed what the program the person wrote. Now, I expect equality to be what's called symmetric, if A is equal to B, then B should be equal to A. That doesn't seem like it's that big of a deal. But that's just a property of, however we choose to interpret AX and BX. And we haven't said anything about that yet. So it's really important to honor what exactly was written, right? As you've already noticed in this course, details matter a lot. Okay. 2 more little quizzes and then I'll wrap up this video. What AST corresponds to 5 minus 3 minus 1? And because I'm a cruel person, I haven't put any parentheses down. I will give the hint, though, that arithmetic operations are by default left associative. What that means. Pause the video. So, true story. I when I was in an undergrad and before and heard the terms like right associative and left associative, I just would ignore them. I would just glaze over. I was like, well, that can't be important. I'll figure it out as I go. And then I would occasionally discover that I needed to write parentheses or just have bugs. Right, this would be a thing that would happen. And much later, embarrassingly later, maybe even post PhD, I don't remember, I realized that associative is a really simple idea. If you need parentheses to disambiguate, which side do they go on? If someone says right associative, it means you put them on the right. If someone says left associative, it means parentheses go by default on the left. So if arithmetic is left associative, that's really the same expression as this. Oh, okay, chill. Let's take a look. So it should look something like this. Which type is it going to be this time? Oh, well, they're all numbers, so something like this. And because the parentheses go on the left, we'll sort of be stacked leftwards. Another bug you might have gotten by now would be doing something like this. It's super tempting, right? It's just the number 1. Come on, what's the big deal? But this has to be of type AX. And the way you say, oh, I'm a number expression is by wrapping it in that constructor. Super easy mistake to make. I routinely make it whenever I'm programming. It's the type checker actually does usually a pretty good job of being like, hey, did you mean to put a constructor on there? And fixing it up for you. Okay, so this is the right answer. You might have gotten something a little different. You might have written something like this. Right? This is the right associative version. Right? And that corresponds to 5 minus 3 minus 1. Right? Which is different. So 5 minus 3 minus 1, this guy, is 5 minus 3 is 2, minus 1 is 1. Whereas this is 5 minus 3 minus 1. It's 5 minus 2. That's 3. Right? Yeah. Okay, last quiz. We'll wrap it up. Consider the following AST. I don't know why these show up. Consider the following AST, ignoring those square brackets, please. What mathematical expression does it correspond to? Let's go the other way. Let's unparse, or as it's sometimes called, pretty print. As in to say, to take an AST and render it nicely in the way that a human would want to consume it. Pause the video. Okay. This is long and maybe a little bit tricky. So let's see. So it's a series of pluses. So that's good. So we can see that. So it's 2 plus, and then now it's a subtree. So I'm going to do a parenthesis 0 plus 0 plus 1. You see how that works? So the further nested you are in the tree, the deeper you are in the parentheses. This is like a fully right associated addition. Now, it doesn't matter, right? Addition is what's called associative, meaning that it doesn't matter what order you add things in, like what precedence you add things in, you'll get the same answer. So if you wrote something else down, like if you wrote this down, that's morally correct, but not technically correct. And this class really focuses, I think, on technically correct, for better or worse, as computers tend to in general. So this is not quite correct because look, the way this expression was written, the whoever provided this program wrote it associating to the right with the nesting on the right rather than the left. That's just the program they wrote, right? And while we expect in our informal understanding of how arithmetic should work, we expect that it doesn't matter. It really depends. Who knows how AX works? Who knows what people are doing? So the right answer here was the one that had the parens all over. Okay, hopefully that helps. If you're stuck on any of these, Try writing them down. Think about them. Maybe share them with friends, or put them on Zulip. And I'm happy to be your parser or unparser as necessary until you figure out exactly what's going on here with these ASTs. It's a super powerful idea. Once you know about it, I think it sort of like lets the syntax of your actual programming language fade away a little more, and you think a little more in terms of like, well, what are the parts here, and how do I need to assemble them? And you focus less on like they use a bar and not a semicolon, and I'm upset about that because it's just concrete syntax. It's just not that big of a deal. Okay, great. We have 7 more videos coming, walking through a bunch of interesting features of ASTs and evaluation and things like that. The next ones will be about a simple evaluator, and we'll work our way through. Looking forward to it. This should be a fun day. See y'all soon.